University, talking on behalf of the Alpha collaboration, I guess.
Thank you very much. I would like to thank the organizers for the kind invitation. My talk will have 3 topics. First, I will talk about our computation of the strong coupling. And then the second part is meant to tie up some potential loose ends that this calculation had. And this will also set the scene for a neat little idea how to compute the strong coupling in a different way. So the first part is already more than 2 years old, and it's all published. The final result is in here. I will give a very quick walk through this calculation. Let me start with a few things that you all are very familiar with, mainly to fix our notation. I will alternate between alpha and G bar for the strong coupling, and it has a dependence on the renormalization scale that is given by this differential equation, and the beta function is completely determined by the theory. Can be also computed in perturbation theory like this. And then to know the scale dependence of the coupling, you need an initial condition for this equation, or alternatively, a value for the lambda parameter in MEV. The lambda parameter is defined like this. So if you know the coupling at some scale, mu, you plug it into this expression, and this will give you the lambda parameter in units of mu. You can also evaluate this equation with 2 different values of the coupling and form the ratio. Then this will give you the scale ratio between the scales associated with the 2 values of the coupling. And a special case for this for us is a scale ratio of 2. So you choose couplings such that the scales are different by a factor of 2. Then the value that the second coupling has is called the step scaling function. And the step scaling function, if you know it for all the arguments, contains the same information as the beta function, but is a bit more suited for numerical methods. The main goal here is to get a value for alpha in phi flavor at the Z boson mass to be able to compare with other determinations and as an input for high energy computations. A simplified way of how this works on the lattice is the following. You would choose some quantity that you can compute in the continuum limit from Lattice QCD, and for which you also have a perturbative expansion. And then you set this equal and solve for the coupling, and this gives you this coupling. Now, there are a few challenges. So this quantity can be, you can imagine, for instance, the force between 2 static quarks at some separation. And then this will depend on the separation. And such quantities always come with an associated energy. In this case, this would be 1 over the separation. And in order for this perturbation theory to work, you need to put the renormalization scale similar to this typical energy scale. And this means that you want to go to high energies on the lattice in order for this perturbation theory to be reliable. But at the same time, you have finite lattice spacings. So you want the lattice spacings be much smaller than 1 over E. And since this perturbation theory is probably done in infinite volume, you want to also have a large volume, which means that L is large. And then L over A is very large, which is challenging. A slightly different approach, but it's very related, is to get rid of the MS bar coupling and work with the coupling that can be defined non-perturbatively. For instance, one such thing would be the QQ scheme, where the coupling is given by the static force made dimensionless by multiplying with the distance squared, and then normalized such that at tree level it agrees with all other couplings. Now, since on the lattice you can compute this for different distances, this gives you directly access to the scale dependence of such a coupling, and you can so you can construct the beta function of it and plug it into this phi function to get the lambda parameter in this scheme that then can be translated into MS bar scheme. But again, this has the same challenges that you have a windowing problem that you want the volume to be large and A to be much larger than this distance r, but this distance r should be much smaller, and this distance r must be very small for perturbation theory to work well. One way to get around this windowing problem is to go to finite volume renormalization schemes. And this works in the following way. You define a non-perturbative running coupling that runs with the box size of your system. So you put yourself deliberately in a finite volume. And in such schemes, it is just enough that L over A is large, which is easy. These finite volume simulations are cheap, but whenever you want to study a different renormalization scale, you have a new simulation to do. And also, you don't get rid of these large volume simulations that are expensive because you need them still for scale setting. The boundary conditions that you choose are now part of the definition of the scheme. And a particular choice that we like to use is the Schrödinger functional boundaries, which means periodic boundaries in space directions and Dirichlet boundaries for fermion and gluon fields in time. This has several advantages. One is that, for instance, you can simulate at 0 in the Carrel limit, which is usually not possible. In this Schrödinger functional, there are many ways to define a finite volume coupling. The traditional one is the Schrödinger functional coupling, which is more or less the response of the system to changes of the boundary conditions. And a newer development is the gradient flow coupling, which is a Young-Mills action density built from fields that are a bit smeared out. And there is a finite volume variant of it that was introduced here. Now, if you are able to measure finite volume couplings in Lattice QCD, to get the scale dependence of these couplings, you construct the step scaling function. And this works in the following way, usually. So to remind you, the step scaling function is the following thing. If you have a value of the coupling that is u at the scale mu, then you change the scale by a factor of 2. The value that the coupling then has is 1 point of the step scaling function. And in Lattice QCD, you can compute it in the following way. You choose a value of u. Then you tune for different lattice resolutions the bare simulation parameters, the bare mass, and the bare coupling, such that the renormalized coupling is u and the bare renormalized mass is 0. Then you, at the same simulation parameters, you just double the number of sites, which doubles the lattice box or halves the scale, and compute the coupling here again. And this will be the step scaling function, but it is different for every lattice resolution, so you need to make a continuum extrapolation in this direction. And this finally gives you one value of the step scaling function. And then you have to map out the u dependence of this thing. The result of such a calculation is shown here. So these are these continuum extrapolations. So each point that is red here is a pair of two simulations. And we do it for this SF coupling and for the GF coupling. The GF coupling at lower energies, the SF coupling at very perturbative energies. And one advantage of this finite size scaling methods is that these continuum extrapolations, they are relatively easy, especially with this coupling. This is absolutely flat. With the gradient flow coupling, it's a bit more difficult, but it's still linear in A squared. This is very controlled. So once you have the continuum values for the step scaling function, you have to somehow interpolate them, or you can directly go to the beta function. You make an ansatz for the beta function and fit the parameters that you have in the ansatz to these data points. And this will then result in what is the main result of such a calculation, the non-perturbative beta function in this particular scheme. So this is a non-perturbative beta function in the gradient flow scheme up to very large values of the coupling. And then for the SF scheme, we do it only at high energies. They don't need to agree. They are different schemes. But they should, at some point, approach the universal two-loop result, which the gradient flow coupling does towards the end here. But for low energy, it sticks to the one-loop line and not the two-loop. while the Schrödinger functional coupling in the range where we computed is just on top of the 3-loop Schrödinger functional scheme result. Now, when you know the beta function, you can take some value of the coupling that you choose by yourself and plug it into this phi function that I showed earlier, and this will give you the lambda parameter in units of the scale of this coupling. So if you know already the beta function, you take this 11.3, you run, and you get the lambda parameter in some units that you don't know yet. Well, originally you get the lambda parameter in the gradient flow or Schrödinger functional scheme, but you can translate them the lambda parameter. This is easy. The last step that is missing is to compute what this L hadronic, the box size, is in Fermi. And this is an expensive piece. It involves the scale setting. So what we need to do is we need to determine a dimensional ratio like this, where we have this L hadronic times something that can be also measured experimentally. And for this case, we come to a result like this. And then you divide this by the physical value of this combination of pion and kaon decay constants and obtain a value for this box size in Fermi, and therefore the lambda parameter in physical units. So this is where the experimental input comes from. First, you need, for instance, the pion mass and the kaon mass to know what the physical mass point is, and then one additional quantity to set the scale. And these are all low energy quantities. Yeah, and the result of this is that in 3 flavor you get this value of the lambda parameter. And to get to 5 flavor, we rely then on perturbative decoupling, which will be the topic of the next section. So there are 2 points where we want to make sure that we don't introduce systematic errors due to the missing of the charm quark. First of all, in this determination in large volume of these low energy quantities, we have this theory with just up, down, and strange quark and not dynamical charm quarks. And we need to assess what is the mistake that we make by doing this. And the second part is this perturbative decoupling relies on perturbation theory at a relatively low scale, like the charm mass. And we need to find out whether this is okay. So this omission of a dynamical charm quark is, in almost all the cases, B quarks and top quarks, has its foundation in this effective theory picture. If you have QCD with NF flavors, but out of this NF flavors, NL are light, and the remaining ones are heavy and have a RGI mass M, then you can, and you are interested only in physics much below the scale of this mass, then you can set up an effective theory, which has a Lagrangian that looks like this. At leading order, it's just QCD with the light quarks. And then you can improve it systematically by adding higher dimensional operators with free couplings. And they will be suppressed by inverse powers of the quark mass, of the heavy quark mass. So this effective theory will have 3 parameters that are in this thing, the coupling and the light quark masses, and then for every such operator, omegas. And to make it work, to really describe this thing, you need to fix all these parameters such that a set of physical observables is exactly the same between the 2 theories. So you pick up renormalized dimension 1 quantities. I call them S, as many as you have 3 parameters. And this fixes what you have to put into these parameters. And then the idea is that any further quantity will still be the same between the 2 theories up to errors that depend on where you truncated this effective theory. So if you cut after just the leading order QCD Lagrangian, you expect inverse powers of the mass of 2. To to test this, we put ourselves in a toy model, which is our fundamental theory is QCD with 2 heavy quarks and 0 light quarks. And in this case, the effective theory to leading order is a pure Yang-Mills theory. This has a lot of advantages numerically. For instance, with just heavy quarks in this fundamental theory, there are no light pions, and we can simulate in boxes that are not so big. And this, in turn, allows us to reach very small lattice spacings that are necessary if you have a large mass, because A times M is a typical size of lattice artifacts that you will deal with. Moreover, simulation in pure Yang-Mills theory, so in the effective theory, are very cheap. And by having 2 heavy quarks, we also enhance the effect that the decoupling has, so we might be able to see the effect better. And this should give us at least an order of magnitude of how big such effects could be at, for instance, the charm mass. So in pure Yang-Mills theory, a dimension 1 quantity like SL is always proportional to the lambda parameter, because that's the only way a dimension can come into play. And this means that if you form ratios of 2 dimension 1 quantities, this lambda parameters drop out. So this thing has no lambda parameter in it and does not depend on the matching. So without doing any matching, you can directly compare ratios in fundamental and effective theory, and they should be equal up to these order m to the minus 2 effects. And now you just need to select some quantities that are precisely measurable. And there is a bit of a problem in pure gauge theory. There's not so much things that you can look at. You could look at glue ball masses or the static force, but all these are not precise enough to resolve these effects. Where one can resolve these effects are a bit artificial quantities that again have to do with this gradient flow. Let's just say these are renormalized quantities that are properties of the theory and can be measured very precisely, but they are not accessible to experiments. If you now look at the ratios of 2 such quantities, on the left-hand side, you have continuum extrapolations of such ratios for different values of the heavy mass at around the charm quark mass and a bit heavier down to charm quark mass over 8. The black line is the pure Yang-Mills theory. You need to do these continuum extrapolations so you get the value of this ratio in the continuum limit. And then you plot these continuum values as a function of the mass, and you expect this quadratic behavior that you now more or less confirm by the simulations. Moreover, you directly see that, for instance, this point here is the value at the charm quark mass, and it is almost in agreement with the Yang-Mills theory, and the difference is the size of this power correction to the decoupling. So these seem to be very small, and this is already with twice as many charm quarks as we would decouple in QCD, in the real QCD. Another thing is this question about perturbative decoupling and how well it works at the scale that is given by the charm quark mass. So the decoupling relations tell you that in order to have these effective and fundamental theory matched, you need to choose the coupling in the effective theory in such a way. This can be computed in perturbation theory. To leading order, it's just the one in the fundamental theory, but then you have powers. And a particularly convenient scheme to do this computation is MS bar at a scale that is chosen such that the renormalized coupling at the scale is equal to the scale itself. In this case, the first coefficient vanishes, and all the coefficients up to C4 don't depend on the mass. The mass dependence is gone. And also it's known to 4 loops, or for our case to 3 loops, because we decouple 2 quarks simultaneously. If you have a relation between couplings, you can also turn it into a relation between lambda parameters just by, well, you can put this couplings into this phi function. This gives you the lambda parameter in units of mu, but the mu is the same in the numerator and denominator, so it cancels, and this gives you a relation between lambda parameters. And this is a factor that we need to multiply onto our 3-flavor result to get to the 4-flavor and then later to the 5-flavor result. So this is really what we need to find out whether it is well described by perturbation theory or not. P itself is not so easy to get at, but what is pretty easy to determine is a derivative of P by the mass, or this particular combination here that is called eta m, or the mass scaling function. And the reason why this is relatively easy to compute non-perturbatively and also interesting is that if you look at this equation, in the fundamental theory, the ratio between the result at a mass m and in the chiral limit, if you replace this SF of m by the effective theory SL and divide out the lambda parameters and multiply them again, you get this equation, which is a bit interesting because this thing does not depend on S and can be computed in perturbation theory, while this thing, if your effective theory is pure gauge, does not depend on the mass because the lambda parameter that gives the scale to S is cancelled out and the denominator is in the chiral limit. And now if you act with the derivative d by dm on this equation, you can derive something like this. And this holds for any quantity S. So this mass dependence of any quantity S is given by the same universal mass scaling function. But the mass derivatives of quantities we can measure on the lattice, and for some quantities it's shown here. This is again done at different values of the heavy quark mass. These points are the charm quark mass, and these are lighter, and the different colors are different quantities. This is all in the continuum limit already. And now you see at the charm quark mass, we sit exactly on top of the perturbative prediction. So perturbation theory works, but we have large errors here. So we can say for eta, it works at the 10% level maybe. But then if you go from the derivative to P itself, this error shrinks essentially by one factor of eta. And since eta is 0.1, you get down to errors of around 1%. So that's very encouraging. Another way to test perturbation theory is to look at this formula itself. So you form ratios of some quantity at mass m over the chiral limit and see whether this is described by the right-hand side where you use perturbation theory for this. This is shown here for a particular quantity. And you see that this is the perturbative result. So this is for P, but you still have this other factor, and this contributes a big error. So this error band is mainly because this contains the lambda parameters in the 2-flavor and the 0-flavor theory. But still, the data is described by this curve. So this again confirms that perturbation theory for P seems to work at the charm quark mass. Moreover, what you can do now is instead of relying on this Q and measure it, you can fit it. And this gives you a Q value that is much more precise than the one that you knew previously. And now this could be exploited if you know this Q very precisely, and you know, for instance, the lambda parameter in the 0-flavor theory precisely. This allows you to get to the lambda parameter in the 2-flavor theory. And this is the basic idea behind the last part of my talk, how to compute the strong coupling from decoupling relations. And this is all preliminary. So the strategy is the following. This line is just an identity. Lambda 3-flavor is equal lambda 3-flavor times things that cancel. But now we take a very particular value of the 0-flavor lambda parameter, namely the one that you need in order for the 0-flavor theory to be an effective theory for a 3-flavor theory that has 3 massive degenerate quarks. In this case, then this factor is given by this P03. And then for this quantity S, we take something for which decoupling applies. So it will be something that in the quench theory should have the same value as in the three-flavor massive theory, up to corrections of this order. And now the idea is to compute these three factors separately. So this you compute in perturbation theory. This you should know from the three-flavor theory. And this contains all the running from the scale S0 to infinity. And this running you can do entirely in the pure gauge theory. And this is much cheaper and can be done much more precisely than the running in three-flavor theory. And moreover, you can study it at different values of this mass. This is completely arbitrary. It doesn't need to be anything physical. Yeah. The first piece is the simplest. This P for this 0,3 case looks like this. It's a very flat function. And the vertical lines are the masses that we want to study, where we need to read off the values. The second decision is what kind of low energy quantity we use. And we need this mass to be much larger than this quantity and also much larger than lambda parameters. And to resolve physics with these heavy quarks, well, we need also AM time to be very small, which again is a bit difficult, but nothing prevents us to put ourselves again in a finite volume that will allow us to stay with moderate lattice sizes. So we define for S finite volume quantity, namely this one. If we compute our gradient flow coupling now in a massive theory, then it should, and we tune the one in the quench theory to be exactly the same, then the scales are something that this decoupling applies to. So the scale in the quench theory will be the same as the one in the three-flavor theory up to up to the power corrections. So what we want to do is we choose just some scale that is not too high, defined by this gradient flow coupling. Now, to determine this gradient flow coupling at some known scale and a high mass, what we do the following steps. So in the first step, we need to know this scale. This is known from the previous running coupling project where we mapped out the massless coupling. And we know, for instance, that if the massless coupling has a value of 3.95, the scale is 790 MeV. And this is the value that we choose to be our S. But now we need to know what coupling we get when we switch on a mass while keeping the box size the same size. So this came with a set of simulations along a line of constant physics. So we had triplets of lattice resolutions, bare couplings, and bare masses, such that the renormalized mass was 0 and the gradient flow coupling was 3.95 for different lattice resolutions. Now, for the same, from these bare parameters, we can now compute the bare parameters that we need to stay at the same lattice spacing, but turn on a mass. So we will need triplets L over A, a different bare coupling, a different bare mass. And up to order A, the couplings are the same, and the bare mass can be solved from this equation. So you choose Z, which is the mass in multiples of the box size. And then you can, if you know the Z factor and the relation between RGI mass and renormalized mass, you can solve for the simulation parameter. These things are known from a different project about quark mass computations, so this can be done. And also, I wrote down the formulae with order A errors, but you can push this up to order A squared. This modifies these expressions slightly, but it still can be done. Then you continue to extrapolate the massive coupling that you get with these lattice parameters, and this gives you the value of the massive gradient flow coupling at the scale that is this one. And this is the value that the coupling in the quench theory needs, where you start your running and from which you get the lambda parameter. First of all, the continuum extrapolations of these massive couplings for the different masses are shown here. This is Z equal to 2, 4, 6, and 8. So the higher Z, the higher the mass, the better decoupling works, but the more difficult these continuum extrapolations become. And clearly, in these cases, we would like to have maybe also finer lattices to have full control. But for the moment, this is what it looks like. And now you need the running in the pure gauge theory. If you know the beta function, you plug in this value of the coupling, and you obtain lambda 0 over S. And for the running of in the pure gauge theory, I show you a result that I was not involved in. It's by Mattia Dalla Brida and Alberto Ramos, but they studied the beta function of a gradient flow of different gradient flow couplings very precisely. And yeah, we use their result. They are also part of this project, so it's easy. One thing that I should notice is that if you use their result to compute, for instance, the lambda parameter in units of the Sommer scale, you get a value that is in quite some tension with most other determinations. And one should say that out of these, only this old alpha result used finite volume renormalization scheme, while all others use more or less single lattice approaches. So in these, the systematics are much more difficult to control. I don't know how this can be really explained. Anyhow, we now have everything together. So this perturbative factor, this value in GV, and this running in pure gauge theory. And we can, for the different masses, see what lambda 3 we get. And for the lightest mass, we get this. And then up to Z equals 8, we end up here. And this is the old result with the standard technique that I showed in the beginning. So it seems that the method works. You see that the deviation from the standard results can be described by order 1 over m squared, which you expect for the power corrections. And moreover, what's interesting is that the errors in this new technique, this piece can be computed very accurately. It's at 1.6%. The main source of error at the moment is the scale setting, so determination of this thing in GV, which is still in 3 flavor and contains the scale setting and the little bit of running in 3 flavors. In principle, this one could get rid of more or less, and then this limits how precisely this method can get at the moment. But it's all very promising, and with this I'd like to conclude. So the first part was the determination of alpha, which is very controlled systematic errors, and it's nice. But it was done in 3 flavors. We have tested that perturbative decoupling of the charm clock seems to be precise enough for us. And in the last part, I showed a new strategy to determine lambda based on decoupling, which seems to work. And probably the systematics can be controlled in the future. We need to go to finer lattices, but the finest lattices that I showed you there in the continuum extrapolations were just 32 cubed times 64, so nothing too huge. One can probably go to 40, 48, maybe 64. And this should, in the future, allow us to get the very precise value of lambda 3. Thank you.
Thank you. So questions?
So about the decoupling. So I know that in perturbative QCD, you can have the decoupling relation messed up if you use the wrong scheme for alpha strong, such that you have to do the decoupling by hand. And I wonder if anything like that also applies to your non-perturbative analysis.
So we use the decoupling relations in the MS bar scheme, and whenever we use it, we are in the MS bar scheme.
Now, the question is how many active flavors you have in your MS bar scheme. That's the whole point.
Well, we are in this very simple situation where we have just 3 heavy quarks and 0 light quarks.
So your alpha runs with 0 flavors or with 2 flavors?
You mean? So when we compute this factor, in the decoupled theory, we use the 0-flavor beta function. And in the fundamental theory, we use the 3-flavor beta function.
And that works. I'm a bit surprised. Normally, I would expect
sure.
that when you take the coupling limit, everything should be expressed in terms of a low energy observable.
No, so we use this decoupling relation at the mass that we are. All our quarks have the mass m, and we evaluate this relation at this particular renormalization scale m. This relates the coupling in the fundamental and in the effective theory, and then we just plug it in here.
Ah, okay, I see.
That's it.
I understand.
Other questions? Okay, so let's thank the speaker again. So lunchtime until?